Okay, let us continue. The second part is to build a useful tool for the proof of channel capacity theorem. The tool is basically joint typicality. Okay, so we learned typical sequences of length n for x, and we also know how to talk describe typical sequences for y. Okay, so x and y individually we know how to do, and x and y jointly we know how to do as well. So basically, for x, we can talk about hx, right? And then we can talk about the entropy rate. Entropy rate converges to x. Entropy rate converges to entropy of x. And using that one, we can talk about the probability of a sequence X belonging to the typical set. Such probability is upper bounded by 2 to the power of minus n times minus epsilon, right? Or the size of the typical set, is upper bounded by 2 to the power of n h x plus epsilon, like that. And then we can replace this with y as well. So we can talk about y h of y minus epsilon, and same expression replacing the entropy with h of y. And we can also do the same with a pair. We can talk about the pair of vector x and y belonging to typical set. Right? Probability of such set is less than or equal to 2 to the minus n times joint entropy minus epsilon, right? We can also say that size of the typical set is upper bounded by the power of the joint entropy plus epsilon, parenthesis, open and close. So that's the asymptotic equipartition properties for x, y, and xy jointly. This we know how to do from chapter 3. So those are the chapter 3 materials. So that's what we mean. What I mean by we know how to, what are the typical sequences of length n for x, and the typical sequences of length n for y, and also jointly with them, x and y together. Okay, and then I want to relate that to this x and y to these questions. If y is the channel output of input x, is x typical with y? We can ask such question. Is the channel output yn jointly typical with the input xn? The asymptotic equipartition property says yes, right? The chance that these two are not jointly typical is very small. and it is vanishingly small as you increase the n number of channel uses. But what about the vector yn? So far is that comes natural to us since we have studied chapter 3 materials. But here are the new questions, right? But what about a vector yn selected from the output distribution? Is it jointly typical with a vector xn selected from the input distribution? So this is the key question in this in the proof of the channel capacity theorem. Okay, so yn selected from its own distribution, xn selected from its own distribution. They are not related with each other by the channel. In such a case, is this joint, vector, xn jointly typical with yn? So that's the question. Answers to this question are the key questions. Okay. All right. Answers to these questions are the key information for the proof. This will give the most useful tool for the proof of the channel capacity theorem. So the jointly typical sequences, we consider a typical set, and it is the set of all x and y's in the n-dimensional space, such that probability that these random tuples belong to the typical set goes to 1 as n goes to infinity. That means the size of the typical set is upper bounded by this, where the entropy is the joint entropy between x and y. So x and y are connected through the conditional probability. Okay, so connected through the channel. So they are jointly related. Okay, and probability of x prime n, y prime n. The prime here has certain meaning. So x prime n are the vector taken from its own distribution. Y prime n are the vector taken from its own distribution. Okay, so p of xn, p of yn are two random variables that are independent with each other. In such a case, if we take them, put them together artificially, then the distribution of these vectors is vectors jointly is a product of pxn and pyn. So in such a case, this belongs to the typical set of the set of this one, right? Described by the joint entropy. So this is the typical set described by the joint entropy. Is upper bounded not by h, x, and y, the joint entropy given here, but by this one, mutual information. So this is the part that we are going to prove. So the part that we can say is this, right? Up to chapter 3, without this. this one without primes, this is a selection of two vectors through the DMC channel. Okay, so X is sent over the DMC channel, Y is received. So they are jointly combined, right? They have a relation. And in such a case, this is going to be this, right? This is going to be that. It related to this one, right? But here we use primes. They are taken independently from its own distributions, right? Just artificially put them together. And then such vectors belonging to the typical set, which is defined by this one right here, is not going to be the entropy here, but it has to be replaced by mutual information. That's the key idea, okay? We will use this key idea in the forward proof of the channel capacity theorem. Okay. So here are a collection of everything that we have said. So joint AEP. So H prime X converges to HX in probability. That means for each epsilon 0 greater than 0, there exists a number n1 such that n is greater than n1, convergence occurs, right? So convergence means the difference greater than epsilon is less than or equal to a small number, which is epsilon over 3. So I can choose this number in my discretion, right? So I can choose this freely, right? All I need to do is find number n1 large enough so that n beyond this n1 convergence occurs, right? So that's the setup for X, okay? So we can find number n1, convergence occurs. So for n greater than n1, this is satisfied. Now for Y, we talk about H prime Y, the entropy rate, sample entropy, sorry. Sample entropy converges to true entropy in probability, and that statement can be put formally again in this form. So for any epsilon greater than 0, there exists a number n2 so this is an integer, right? So for index converging index, time index, or for n greater than n2, we can find n2 so that this is true. Okay, so that means probability of difference greater than epsilon is less than epsilon divided by 3. Okay, so why I am using divide by 3? Because I'm going to add them all up. So I can choose this any number, right? So I can choose this to be delta. So the right hand side to be, and delta is epsilon over 3. Okay. All right, so I have done this for Y, and I can do that for joint entropy as well. So sample joint entropy converges to joint entropy in probability. That means this statement 3 should be true. All right. So once I have this, then we are in business. Okay, once I have that, we can choose number n, got the convergence index n, which is the maximum of these 3 n's. Then all 3 measures have convergence, right? Shows convergence in this convergence index n, right? So if n is greater than n1, n2, n3, all 3 of them converges, right? All 3 of them satisfy. 1, 2, 3 satisfy. Then the probability of the union of the 3 sets in previous page is going to be smaller than epsilon. So that's what it is. Okay. So you have done that. Then we can say joint AEP is this. Okay. Is this one. Okay. Starting point. So summation of the distribution should be 1. And this is upper bounded because the summation is only over the typical set. And we will replace this with the lower bound, okay, which is this one. So this is lower bounded by this number right here. And once I have done that, I can bring this outside the summation, and the summation over the typical set is nothing but the size of the typical set. So we have done this type of proof in chapter 3. So this is a repetition. And then once I have this up to this far, then move this to the other side. Then we have size of the typical set upper bounded by this number right here. Okay. That's the case that we can easily understand since we have studied chapter 3 materials. Here are the new part. Okay. Now, x prime n, y prime n are independent, but they have the same marginals as xn and yn. So for example, we can talk about joint distribution p, x, and y. X taking values 0 and 1, y 0 and 1, okay? Then we can talk about the marginals. So what is the marginals? Marginal is, so that is 3 over 8, adding the 2, 5 over 8. Okay, that's the marginal for y. So this is distribution for y, and then we can do the same. For each x, we add the 2. So this is 2 over 4, also 2 over 4. So these are the marginals. Marginal for y, marginal for px and py obtained. Now we can talk about the product distribution. The product distribution says this. Let's verify this one right here. So that is when x is equal to 0, which is 3 over 8, sorry, 2 over 4, when x is equal to 0, and y is 3 over 8. So that is so 3 over 16. All right. So that's how you obtain, right? You take the product and then you obtain these numbers. Okay. As you can see, there is a difference between product distribution and joint distribution. Okay. There are difference. Okay. And now you select x with respect to px, you select y with respect to py. That's what the meaning of this one right here. Okay, so you have selected two vectors from this product distribution. And what is the chance this selection belongs to the typical set, which is defined by the joint distribution? So defined by the joint distribution, so this is going to be related with joint entropy. Joint entropy. Okay, so that's what it is. So using this definition, so we add up all xy pairs belonging to the typical set, right? That's the meaning of this event. But this selection is made from the product distribution. So Pxn, Pyn, because we use channel n times, okay? Now, this product distribution, each one can be upper bounded by this and that, okay, with the hx, hy, okay? So this probability is upper bounded by this one, that one is upper bounded by this one. And once I have done the upper bounding, since this is free of x and y's, so they are numbers, so we can bring this outside the summation, and the number of summation is now upper bounded by this measure right here from the previous page, from the result in the previous page. So that one appears right here. So once I have this, then all I need to do is to do the summation on the index. So index here, since I have minus signs, I take minus sign outside, and what do I have inside the parentheses? Minus, and inside the parentheses, what I need to have hx minus hy, plus hy minus xy jointly entropy. Xy jointly, and this is nothing but mutual information between x and y, because this can be written as hx plus hy given x. Okay, so hx, these two cancels, hy minus hy given x, that is mutual information between x and y. So I have this. So probability of x and y pair taken from the product distribution belongs to the typical set defined by joint entropy is upper bounded by 2 to the power of n mutual information. So this probability is upper bounded by this one right here. So you can take away a little bit or add a little bit. Okay, so that's the probability. upper bounding, upper bound of the probability of selecting X and Y from the product distribution. Okay. So this is the same thing illustrated in graphics. Okay, so I enumerate all typical xn's right here. So I can enumerate, let's say, first one, second one, all the way up to 2 to the power of nhx. I enumerate all of them. So each one, right, is a sequence, okay, of length n. I enumerate them right here, okay, and I send these sequences over the channel. Then, because channel is noisy, I have spread of y's. You send this one, I have a spread of y, spread of y, spread of y, and so on and so on. So when I send each one over the channel, then I have a range of outputs, right, instead of single ones, right? So this range of output is represented by these scattered dots, right? For each x, I have a output distribution, okay? And when I send this one, the output located right here could be possible, but it is not typical. So these are the typical outputs. So that means if I consider x and y jointly, these are the typical sets jointly, x and y jointly. So these are the typical set. Outside of typical set is possible, but very rarely occurs. So these are not typical set. These are the typical sets of pair x and y. Okay, so these are the typical sets for pair. Okay, outside of this typical set is possible to occur, but very rarely, right? So once I have done that, I can take the ratio between the size of the joint typical set, which is this one, and divided by the every possible pair of sequences. So that is 2 to the power of nhx here, and then y is also 2 to the power of nhy. So total volume, I mean total number of sequences in this domain is product of the two. So they are possible to occur, but only these typical sequences, jointly typical sequences, are typically occur, right? Are the ones that typically occur. Okay, so this, if you take the ratio, then that is nothing but the 2 to the power of minus n mutual information. So that is the reason if we select a pair blindly, let's say choose any pair of sequences in this space, that is going to be any one of these, and then the probability that selected sequences, sequence pair x and y belong to this typical set is going to be upper bounded by this number. Okay. So that's the graphical illustration of jointly typical set. Okay. And let's move on to the third item in the next video. So the next video is going to, in the next video, we are going to prove it, prove the fourth part. Okay.